Hi, I'm Tuvia Goldstein from Chicago, Illinois, and I'm a first-year computer science student at Yeshiva University.
I'm Binyamin Jachter from Teaneck, New Jersey, and I'm a second-year comp sci student.
I'm Seth Jacobs from Bergenfield, New Jersey, and I'm a second-year computer science student.
I'm Yonatan Olshin from Woodmere, New York, and I'm a second-year CS student.
This summer, we participated in the Industrial Software Development course offered by Yeshiva University,
where we had the opportunity to learn from expert mentors,
work as a group,
interact with technologies we have never seen before,
and developed our first distributed system.
Yoel Spots worked with us this summer as the mentor for this project.
Yoel lives in Atlanta, Georgia, and is a senior software engineer for Elastic.
He consistently challenged us and helped direct the development of our application.
And we are extremely grateful for all of his help.
Over the course of the summer, we built an application for a distributed bookstore. A bookstore has a repository of books on which the CRUD operations can be performed. You can create a book, read the information of a book, update the information of a book, and delete a book from the repository. The repository is persistent, and the inventory gets saved to disk even upon shutdown. To partition the data evenly, we have one bookstore per server in the network. We then have a hub to maintain the network. This is a diagram of our application. We have 3 bookstores here on 3 different servers. Each bookstore alerts the hub when it joins the network, and the hub tells the other servers of its existence. Then each of the servers can communicate with each other independently.
Some of the challenges we faced in the course over the summer were the nitty-gritty of Spring Boot magic, which was a black box for us, where we didn't exactly know, where we didn't exactly understand the mechanics behind all the annotations. So we had to do some research on the Spring Boot technology in order to familiarize ourselves. Another challenge was learning to work as a group. The third challenge was implementing a distributed system, getting all the computers to communicate with each other. And a fourth challenge was debugging across multiple servers. Oftentimes we didn't know exactly where or in which server something went wrong, so we did tracking. So we tracked the requests using logging.
The architecture of our program is based around Spring Boot, which we used to be the basis of our web application across the multiple servers. We use JBA databases to keep our data persistent on shutdown by storing the data in both storage as well as memory. We then partitioned the data across the multiple servers, with each server being its own bookstore. CRUD operations are available to be performed by clients no matter which server they're connected to on the network. They're able to create, read, update, and delete books from any particular bookstore. We do this by returning redirects to the client so that way they can connect to their intended bookstore. The hub is essentially the map of all our servers, storing the addresses of each server and keeping the server-side maps up to date. We do service discovery as well, keeping check on all the servers to know which ones are up. We also do leader election, where we select the leader for specific operations to keep the data from being written without multiple sources writing to the same data at the same time. We do health checks upon the leader to make sure that the leader is still functioning as intended. If it shuts down or is running too slowly, we will change the leader from the hub side. Batch requests are done by the leader, but they will take multiple requests all at once and distribute them into individual requests using request forwarding. We use Resilience for J as a library for our resilience. We use retries, where we continuously retry every call to, or the same call to, a particular server. We use rate limiters to prevent DDoS attacks and the like by limiting the amount of input any particular operation will do. And we use a circuit breaker to stop waste of resources on known down servers. And only once they are known to be up again will it allow it to go through. Finally, we have distributed logging, which gives an ID to each request made, so that way we're able to track every individual request across the multiple servers in our network.
In summary, we built a distributed system that can handle the major CRUD operations. Our data is both persistent and partitioned. The hub can handle leader election as well as service discovery. Everything is resilient through the Resilience for J library. And finally, we track everything through the distributed logging system we came up with. This can best be demonstrated with an example. The four of us will create a network of bookstores, me from my home in Chicago, Seth from Bergenfield, New Jersey, Yonatan from New York, and Binyamin from Teaneck, New Jersey. In 1917, in New York City, Gilbert Clifford Noble and William Barnes became partners in their first bookstore. Located on 15th Street, this small store quickly became a staple of the community. This store would have needed a way to keep track of their inventory, and our software would be perfect. Using Postman, we will create a bookstore representing the small shop on 15th Street. So as you see, Seth has all the information ready to go, and he's now going to post it to his server. If you notice, the JPA repository auto-assigned him the server ID of 1. As the store grew more popular, they had to add more and more books to their inventory. For example, The Great Gatsby became very popular upon release in 1925, and any bookstore would have needed to stock it. So Seth is now going to post it to his newly created bookstore. As times changed and inflation hit, the price went up and therefore needed to be updated. Seth is now going to demonstrate updating just the price of the book. As you can see, the only thing that's changed is the price. After facing challenges from Baptist groups, The Great Gatsby was temporarily removed from bookstores and therefore needs to be deleted from our inventory. As you see, Seth successfully received the 204 status code indicating that it was deleted. As the bookstore grew, customers requested the ability to browse through the ever-growing inventory. Seth is now going to demonstrate getting a collection of all the books stored in his store. As you can see, he has 1984 by George Orwell, as well as The Way of Kings, and finally, Charlotte's Web. In 1932, at the height of the Great Depression, the bookstore moved its flagship location to 18th Street and 5th Avenue, the place it would stay until it closed in 2014. Seth is just going to demonstrate updating one part of the information for the bookstore itself. As you see, the only thing that's changed is the street address.
In the 1940s, the company began to expand and open bookstores in Brooklyn and Chicago. So let's open a bookstore in Brooklyn. As you can see, the post is successful with a server ID of 2. Having one server for 2 bookstores wouldn't work for various reasons. For example, if anything were to happen to that server, we lose access to both stores. If both stores were trying to update the same book, they would overwrite each other. Doubling the stores means doubling the people who require access to the server. If too many people are accessing the server at the same time, the server can slow down or even crash. Additionally, doubling the stores doubles information that needs to be stored in the server. Therefore, we posted Barnes & Noble Brooklyn on a second server. However, when the bookstore in Chicago opened and needed to join the network, as demonstrated by Tuvia right now. Good. So we needed to find a way for all 3 servers to communicate, and that is when the hub was born.
The hub became our conductor of communications between the stores. Whenever a store is created, it lets the hub know that it exists, and that is how you can reach it. The hub then responds with the information from all the other stores, so that way that new store can be up to date with everyone else. And then the hub then informs all the other stores about the newly added server to the network. This allows for communication between all the stores with no reliance on any one particular server for an entire business. We'll first look at the H2 console, where we can go through the data store of the hub. You can see our 3 stores, New York, Brooklyn, and Chicago, being stored with their IDs ready for them to be mapped out as necessary. We'll also go through the logs of the hub, where you can see here we have each time a bookstore is added, we send the new address to all the current bookstores inside the server.
When a customer walks into the Brooklyn store looking for a book, he may be disappointed that this store doesn't carry it. Lucky for him, the store in Brooklyn can pull up the inventory of the store just over the bridge in New York City and can purchase the book there. So Binyamin's now going to demonstrate getting all the books from the Manhattan store. So as you could see, the get was successful. The store in Brooklyn was able to get all the books from the New York City store through a redirect.
And this man no longer, once this man purchases the book, we no longer want it to appear in the inventory of the bookstore in New York. So the Brooklyn store will delete it from the New York store for them, so that way they can't sell the same book twice. Yonatan here is demonstrating the deletion of a book via redirect. As you can see, he gets a 204 no content status code, signifying a successful deletion.
When Barnes & Noble published The Wonderful Wizard of Oz by L. Frank Baum, they wanted all their stores to carry it. Instead of each store individually having to post it to their inventory, the corporate office just posted to all of them at once. There we go. So Tuvia posted one book to stores 3 and 4. And you can see each book has a different store ID. In 1986, Barnes & Noble bought out the B. Dalton bookstore and now needed to distribute all these books amongst their already existing stores. Instead of needing to post one book at a time, they could post them all to all the stores at once, doing a batch request. Here we see that Tuvia posted multiple different books to multiple different stores with one request. With all these functions for the batch requests, we could run into a problem if multiple servers are trying to add a bunch of books to the same store at the same time. To prevent inconsistent data where multiple servers in the distributed system might be updating the same piece of data, we need to have a lock such only one server can update the data at a time. Therefore, we designated a server to be our leader. This server handles all batch requests no matter where they came from. When one store calls a batch request, it checks to see if it is the leader. If it is not, then it passes that request on to the leader in order to complete it.
The hub constantly does health checks on the leader. If the leader server is down or is going too slowly, they'll assign a new server to be the leader. This ensures we always have a leader up and running, so that way our batch requests can be completed in a timely manner. All requests are logged into the system with a request ID, so you can trace the request as it goes from server to server across the network.
When the Chicago store loses power for a few moments from one of their infamous windstorms, at the same time as another store tries to call it, the store can retry that call until the connection reestablishes. Tuvia will now demonstrate a retry. So as you can see, when the server is down, it continuously retries the connection. Once the blackout is over, however, we are able to connect. So let's just wait a few seconds until the server is back on. In the meantime, if you notice, the request ID stays the same for each retry. Okay, as you can see, the request is handled once the server is back up and the same request ID is logged as successful.
During the infamous Great Northeast Blackout in 2003, different parts of New York City lost power for up to 4 days. Instead of allowing the other stores to waste resources trying to call the New York City store for what could be multiple hours to days, we implemented a circuit breaker that would see that the New York City server is continuously down and pause all calls to that server until it restarts. Tuvia is making a call to the New York City server. As you can see, the New York City server is down and the connection fails. It is going to retry 10 times, but then it's going to realize that the New York City server is not coming back anytime soon. When that happens, we will enter our fallback, where we will ignore the call to this server, and we will continue with all other calls. Now we've entered the fallback. We're going to ignore this call and continue to other calls. When Tuvia tries to call the New York City server again, it immediately checks once, and then it immediately enters the fallback, as to not waste resources on our retry when we know it will not be completed.
In a scenario where the hub goes down, most functions should continue to work. Each server has the knowledge of all the other servers in the network, as well as the knowledge of who the leader is, and therefore can continue without having access to the hub. However, While the hub is down, no new store can be created, nor can a server be restarted. If the leader goes down as well, the network will be leaderless until the hub assigns a new one, therefore making batch requests unavailable at that time.
Unfortunately, sometimes a store is forced to close down and therefore needs to be removed from the network. When a store is deleted, all other servers are given that information to remove the newly deleted bookstore from their own maps. So Seth is now going to demonstrate deleting the bookstore. If you notice, we have this delay, which should take about 15 seconds. It's because the bookstore needs to first delete its entire catalog, and then the hub must inform the entire network of the newly deleted store. As you can see, he successfully received the 204 status code. Today, Barnes & Noble has 627 stores across the 50 United States, and our software would be perfectly capable of handling their entire chain. Thank you for listening, and we'd be happy to take any questions.
So we'll definitely open up for questions. I just want to note a couple of things, just in terms of kind of the initiative that the fellows took. In terms of the technical aspects, a couple of things that were their idea completely was, number one, the idea of the hub kind of acting as the central orchestration for service discovery and for leader election. That was completely their idea. I described the problem space and they said, oh, we could solve that through a hub. And secondly, the health checks was completely their idea. When we talked about leader election, on their own, the initiative came, well, what if one goes down? How are we going to know about it? And they intuited and came up with the idea of health checks, of constantly pinging on a schedule, periodic basis. So I just, again, kind of bragging on their behalf as to the initiative that they took.
So I'm super curious. Whenever I build something like this, like there's always like a long list of stuff where I'm like, oh, I should have done this, I should have done that. Like this is going to be my next step. Like this is going to be like the next thing. Like what are some things that y'all were sort of like, yeah, we'd love to add this, but like just don't have time or is not in scope, or like, you know, if you're going to extend this, like how would you extend it? Like what's yeah. Any thoughts on that? Is that too general of a question?
No, that's a great question. We know our point of failure is really at the hub, which it's true that the basic network already will stand and can stand on its own while the hub is down. But if the hub does go down, as we mentioned, there is no way for new servers to be added, nor can they even restart, because a part of the restart is they reclaim the map of the network from the hub. So we would have to do some kind of redundancy or some other way for them to be able to find their way to the network if on restart about the hub. So we know that that's our main point of failure. So that would be probably something that we would want to add.
Something we also spoke about a little bit was authorization and controlling who can access and update which pieces of information. So that would be really great to add to the system.
Another thing, which was a little further down the line, but we spoke about making a GUI last week, like a graphical user interface, which you thought would be a lot cooler.
Out of curiosity, like how did you implement leader election?
So we started off with the first server that's up gets to be the leader. And then we did health checks afterwards. So if it goes down for a minute, then it will pick the next leader, the next server who came up to be the leader. Then we said, well, there are times that no one's going to be on, but the hub's going to be up. So who gets to be the leader? So then when someone comes up, then he gets to be the leader. So we did sort of by first come, first served basis.
So have you implemented the logic like from scratch? Because usually like you have a bunch of servers, they all need to decide together on the same leader, right? So
yeah, so the hub picks a leader right away. And then every time a server comes up, it tells all the other servers that the person who was assigned the leader is the leader. And then if the leader changes throughout, the hub sends a message to all the other servers saying, we have a new leader, change it to the new guy.
My question would be in the same direction. What happens in some weird cases? For example, the leader changes, but some of the bookstores don't get the message that the leader has changed? Or will it kind of all the time update this, or how would that work?
I believe we have retries on the sending out of the leader. So if it doesn't make the connection in the same way we have resilience going from bookstore to bookstore, we have resilience going from the hub sending out the leader. So even if it doesn't work one time or two times, we have it set up that eventually it'll get there before it can actually start reconnecting again.
Yeah, so will the hub track if everyone has a knowledge that they now have a new leader?
I don't think we have specific logs for that, but we can probably quickly implement like this person knows and this person knows and this person knows.
Thanks.
Are you all familiar with the CAP theorem in your university stuff? Okay, so effectively the TLDR of it is, at most with a distributed system, you can either have consistency, so at any point in time all the data is consistent across your entire infrastructure. Availability, meaning that any point in the infrastructure is always available, or partitioning, where it can survive a network partition where certain components can't talk to each other. Thinking that through, where do you think your application would stand on that? Like, what trade-offs do you think you've made through that design?
So I would say that by doing the partitioning, we've definitely given up on speed, as it relies a lot on redirects and keeping everyone separated. And therefore not everything is consistent in everyone knowing where everything is, especially with leader election. As Dominic had pointed out, we have to go and tell every single person individually, or every single server rather, that the leader had changed. But with that being said, it still is relatively efficient, but I would say that keeping our traffic down is probably the strongest aspect of our partitioning. It keeps each bookstore on its own, ready to go without being bombarded by any particular amount of users.
Yeah, so in the end, each bookstore could work on its own, right? If it would survive and continue responding, even though it might not have access to all the information anymore.
100%. We've had it before where once the server's up, if every other server shuts down, it totally works just fine. It'll try doing those redirects as necessary, but once the circuit breaker trips, it'll just say, nope, can't do that anymore, and it'll just return. That's it, sorry. And with that, it on its own, each of the servers can work consistently without any issue.
I have kind of a multiple choice question, or it's sort of, yeah, I'll just ask it. What was either, for each of y'all, and I'm sure the answer will be different, like what was either the toughest part of the project to get your head around, or your favorite part, recognizing that a lot of times those two things can be the same?
So my favorite part, and I think the toughest part also, was just getting the servers to connect to each other, like getting our individual machines to actually be able to interact and sending a request across machines. It was my first distributed system, so it was just super exciting when something like that worked and it went through, and to see the results. It was challenging to get it to work and get all the different pieces to go together, but when it went through, that was something very, very cool.
The toughest part for me was definitely learning how to work as a group. I've never really done a group assignment like this before with a full team, and we all had different strengths and different ways of thinking about a problem, and thinking about it together is definitely a challenge, but at the same time, very cool. I probably enjoyed that the most also, but I also enjoyed the puzzle a lot. There's a lot of different pieces that had to be at play here, and figuring out like how each one fits and where it all goes was a lot of fun.
I would say that definitely the point that Tuvia made, which was once we had like the network working, it was pretty crazy. It took like a while figuring out how to like set up the hub for port forwarding, so we consistently had the same domain constantly running, and we can just put that in environment variables, and then that was it. So that was really fun going through that, and like it was really nice. Wow, we have something going. Chicago, Tuvia in Chicago wasn't originally in Chicago. He was also in New York. So it was like all in the same area. And then like the next day after we had implemented it, he ended up going to Chicago. And it was like, wow, we now have like across the country something going on. That's pretty cool. That's pretty crazy. It was really, really cool. Hardest part for me, I'd say, was when we like get stuck on something and we just have nowhere to go. So it happened a lot with like resilience for J. The circuit breaker did not have the best documentation. So we didn't really know what was going on when we were trying to implement layering the retries with the circuit breaker. So we'd implement the retries, it would go over and over, and some of them would require a particular exception to be thrown, but others would not want that exception, but a different one, but only one of them would catch it. So then the circuit breaker would like trip based on something completely different on the first try. And it was really hard to finagle with that. So we had basically, after wasting a day, we had gone to Yoel and been like, we've got no clue what's going on. We've Googled all we can and we really got no clue. And then Yoel wasted a day of his going through that, trying to figure it out. So, stuff like that. That was probably the most frustrating, when like they were just was a dead end because the research wasn't going anywhere particularly well.
I think my favorite part of this, I think a little bit similar to what Binyamin said, was just the fact that all these servers from across the country could connect to each other. It's not just, we weren't just running a local host and all the servers on a local host. This was literally across the country. So I thought that was pretty cool. And at the same time, that was also one of the hardest parts, because sometimes the server was down and we didn't even know it, or we kept on getting 502 bad gateways. So it was oftentimes hard figuring that out.
Yeah, a couple of comments there. In terms of, it was completely their idea, like me being the engineer that I am. If I was testing this out, I was gonna, I would have run everything on localhost just with different ports. But they were, you know, their thought was, this is really a distributed system, let's run it as such. And so everybody was running their own server. And so they figured out how to use port forwarding. And I pointed them to ngrok.io, and they made use of that in order to forward requests to their stuff on their local machine. So they really truly had a distributed system, and they figured out how to make that work. The second comment just about what Binyamin said, kind of the analytic, where they would try to figure out something, and it's like, how do you and then once they couldn't figure something out, they would come to me and they'd say, what is going on with the string annotation? What's the magic here? And either I would know it, or just from experience be able to offer them, here's what you do. And you know, they would ask me like, how are we supposed to know that? And the response is, you're really not supposed to know that. That just comes with experience. But that you know, so that's all in a way of saying that they were able to do as much research as they could, and then really only when they couldn't figure it out is when they came to me to try to figure it out. Especially with that circuit breaker, there was some very poor documentation, and they figured out what I would expect them to figure out, and then the other things that I would not expect them to is where I had to step in and be like, and do a little bit of code splunking and trial and error.
Yeah, maybe one question I had in a different direction is, you mentioned for debugging and logging that was problematic, obviously, for a distributed system. I was wondering if you can elaborate a bit more on your logging techniques that you built or set up for this to figure out where something went wrong. And I guess you also had the logs distributed. So how did you have any way to collect them, or how did you solve that?
So with our log statements, anytime a request was made, we gave that request a specific ID number, and then we kept the ID number throughout the request. So if one server called another server, and that server then uses that request on the third server, we'll have the same ID all throughout. So then we could track the log statements. We could see, oh, okay, it originated here, but it ended up going to the server, to that server, ended up there. And we could follow it the whole way through.
We didn't originally have that. So we would sit there debug, and because it's multi-threaded, so like you'd have multiple calls possibly going across the network, especially because with leader election, it constantly is pinging the leader every, say, 30 seconds or so. So we'd be like in the middle of one call trying to figure it out, and then every 30 seconds it would jump to like some completely different method because it got pinged by the like, and then it jumps back, and we'd have to go through that. So only towards the end did we put in the distributed logging, because Yoel had essentially mapped out like where he essentially wanted the project to go. Like we started with this distributed data store not being distributed at all. It was just a data store on local machines, and that was it. And then we built out from there. So us adding in distributed logging only came over time towards the end. So that entire beginning phase where we're just making the network and having the calls jump across was a lot more confusing than it should have been had we had our final implementation put in, which now it's great and we can track and see exactly what's going on.
Yeah, sounds like a perfect way to solve it with this request ID. Maybe in the same direction, did you also do any kind of manual or other testing towards scalability, or did you at least spend some thought on what could be the limiting factor if you want to add thousands of bookstores maybe, or some bookstores with thousands of users, or any other, I don't know, maybe thousands of millions of books in one bookstore, or things like that?
So what we did try was if someone just made like 1,000 calls to one server at like the same time. So we had like a for loop running of just like tons of calls, and to see if the rate limiter and the retry is able to, and the circuit breaker was able to handle all that. And it was, which was very cool. We didn't try expanding to see how many servers would be like the limit of the hub, but yeah.
Okay, yeah, that's cool. That's always funny to see when it breaks down as well. But if you could even handle this, that's nice.
I would also just like to say that it's very impressive that at the beginning of this project, you guys have never built like a web application before, and at the end you have like a distributed system with leader election, with where you had to handle a lot of different use cases. It's pretty cool, like especially like you had a truly distributed system, which with like ngrok.io, everyone like actually using service across, like having communication across the country. It's a pretty cool feeling, like of accomplishment as well. So I think that's very impressive.
Yeah, I mean, the last thing I just want to say, I mean, echoing Mario's words, like it's very impressive. I mean, this is just like really cool to see. You know, especially that you know, this is y'all's first time building something like this. Like it's a lot to get, you know, to get your head around. So it's very impressive, and I hope y'all are proud.
Thank you, appreciate it.
And thanks for the nice presentation.
Yeah, I love the storyline.
Yeah, again, just in terms of bragging on behalf of the folks, I had my kind of outline of a dream list of what I wanted to cover, and realistically I thought we were going to cover about half of it, and they just kept on cranking stuff out, and I had to constantly stay on my toes. Okay, let's fit in a few more things then, I guess. So that was again very impressive.
Thank you very much, everybody, for coming and listening and sharing. Thank you.
Thank you.